Now the topic is basically for this entire program is geospatial technology for hydrological modeling. But I thought let us start with the overview of geospatial technology applications of different aspects of water resources. So this is the first lecture. So basically, first you should try to understand the use of the water. So you know that water we need for drinking, maybe 2 to 3 liters per day, or during summer it may be more. Water for sanitation we need maybe around 80 to 100 liters per day. Water for industries, huge amount of water is required. And water to grow food. This is the amount of water we consume most. In fact, you may be aware that to produce 1 kg of wheat, around 1,500 liters water is required. So suppose you are consuming every day 200 grams of wheat, it means you are consuming 300 liters of water. So you can imagine how much water we need every day. I'm just talking about the wheat. You may be taking rice also, you may be taking vegetables also. So for everything, in fact, we need water. Why only food? We need water for clothes. We need water for specs, we need water for telephone, we need water for mobile, we need whatever you are seeing around you, all the things, actually they are produced using the water. So water is one of the most important thing, and without that we cannot survive. And of course water for irrigation also. But there are certain issues in this country, like we are having 17% of world population, but only 4% of world's water share is there with us. So you can see this anomaly. Second one is around 80 to 85% water is consumed by agriculture. You can imagine, if you see the industry, only 8 to 10%, domestic use only 5 to 7%, up to most you can say 8%, not more than that. But maximum water is consumed in agriculture or in irrigation. Another problem is the irrigation efficiency in India is only 38%. Now you see, if we increase the efficiency of irrigation, let us say in place of 38%, if it is 48%, you can imagine that 10% of this percent of 80% of water, it will be available for what? For domestic use, where generally people are facing problem. Every day your drinking water supply will increase. So that's the reason why Government of India has given an emphasis that we should increase the efficiency of irrigation in this country. You are aware that our population has increased during independence. It was only 33 crore and now it is 133 crore. So you can imagine how much, it is almost 4 times. And that is the reason why per capita water availability is decreased up to a threshold. What is the threshold? Threshold is 1500 meter cube per year. So this is already over in 2017. Now we are heading towards water stress country. They just say, if water availability is less than 1500 meter cube per year per person, then this country is under water stress. And now in 2021, we are under water stress. So this is the issue. So it is not only the natural resources, it's the population also makes a lot of difference, how we are increasing our, problems. Or because of that, we are having exploitation of the groundwater. And you are aware that there is a climate change. So extreme events are increasing. In a day, you are having a huge amount of rain, and up next 10 days, you will not have any rain. So because of this extreme event, either there is a flood or there is a drought. In fact, earlier, when in an area where there is a flood, droughts were not happening. But nowadays, in the same area, there is a flood also and there is a drought also. This is a very unique phenomenon because extreme events have increased. And it is happening because of the climate change. So now we have to again rethink our planning of the water resources, okay? And of course, the biggest problem in this country is the population growth. This is the thing, for example, the water is same in our country, it is not decreasing or increasing. But in 1947, per capita water availability was 5200 meter cube. And now it is less than 1500 meter cube. And why? Because per capita means population is increasing. So these are some issues. So for that, what we have to have a water resource management. Now, few facts, as I discussed with you, Like wheat, it needs around 1300 to 1700 liter of water. Maize, it needs 900 to 1200 liter of water. Paddy, rice, it needs 3400 to 3800 liter of water. Those who are non-vegetarian, meat, it needs 14,000 liter per kg. 1 kg of meat is produced using 14,000 liter of water. This is the calculation based on how much these animals are taking water and all these things. No? And you know that you are wearing t-shirt. So 4,000 liter of water is required to produce 1 t-shirt. Now you tell me, you understand that the importance of the water, how much water we need. Every day we eat wheat, every day we eat rice, every day we eat meat, every day we wear clothes, every day we use laptops, every day we use mobiles, every day we are using. So what is this? Basically they are the they are consuming water in their production. You can imagine how much water we need. Fine. Let us come to the geospatial technology. When we are talking about the geospatial technology, in fact, when we were deciding the topic, we have not, categorically decide that we should go for geospatial technology for hydrological modeling, because geospatial technology consists of all the sources of the data and integration. Like when we talk about geospatial technology, basically remote sensing, which provides maximum data, like all our satellites, right? This is very important. Second one is the GPS, location for anything. Where is the water resources? What kind of water resources? What is the latitude, longitude of that area? We need GPS. Again, it comes from satellites. You know that GPS satellites, US, they have a GPS system, global positioning system. They have system, GPS. But Indian system, you may be aware, IIRS, we have this system also. Some other country like GLONASS is another system. There are many systems, but generally, whatever you are using in mobile, this basically you are using this GPS, but very soon you will have our Indian IIRS system also. But it provides you the information about the location of the resources. Okay. But then another important data is the field data. Lot of field data is required in water resources in hydrological modeling. You need discharge data, you need rainfall data from the field. So all these data, and now all this data is input into a GIS environment. Okay, like land use, land cover, like water body, like road network, canal, drainage, all these things, data is required. Okay, and we feed in the GIS environment. Then we use a hydrological model and we run the model, and finally we get the discharge, and this should be disseminated through the internet so that people can get it. So this entire thing becomes a geospatial technology. Now you understand what is the role of geospatial technology in anything like water resource management. For example, remote sensing is required to get the data of water resources, land use, land cover, dam, canal, drainage, many things. Digital elevation model, GPS for location, field data for, as I told you already, GIS for data input, integration, manipulation, analysis, and finally output, and it goes through the internet to reach to you. So this is the geospatial technology. Now let us come to the first component, which is most important, that remote sensing. So that is basically imaging from space. So you are aware that we have a different, orbits. You may be aware that we have a geostationary orbit, which is 36,000 kilometers. Any satellite which is launched on this orbit is always top of us. Every 15 minutes or 30 minutes data I get. So all weather information I get from this type of satellite, and all communication information I get from this type of satellite. So our InSat 3D, 3DR, they provides cloud information, cloud top temperature information, precipitation information, and we get from this orbit. Okay. Now LEO, low Earth orbit. Geo means geostationary orbit. LEO means low Earth orbit. This is very close, 600 kilometers. All remote sensing satellite, polar orbiting satellite are orbiting in this orbit. For example, Resource-Sat 1, Resource-Sat 2, Cartosat 1, Cartosat 2, Cartosat 3, Reset 1, Reset 2, OceanSat 1, OceanSat 2. All these satellites are running in this orbiting in this orbit. And of course, UAV or like aerial aeroplane, these orbits are there. But these are the major two orbits which we need. What do you get? You see this beautiful agriculture field, you get the forest information, you get the urban, you get the water, all these things. But near real time you get temporal information, because satellite will come again next 5 days. So temporal information. You get the special information from this point to this point, from this point to this point. You get the synoptic coverage, complete coverage. You can cover in a single scene entire district. You can cover in a single scene entire state. So synoptic coverage will be there. It is not like that. Today, what is the condition in a particular place? So it will cover maybe next 700 kilometers, you will find the condition. So synoptic coverage you will get. Okay, so these are the advantage of remote sensing. Now, our satellite system. India has a very robust and very important satellite system, and we have categorized into 4 categories. One is the Earth observation system for land and water, Earth observation system for high resolution cartographic information, Earth observation system for ocean, and Earth observation system for the weather and climate. So for land and water, you are aware that this is our main satellite, ResourceSat 2. It has a 3 sensor, List 3 with 23 meter resolution, List 4 with 5.8 meter resolution, AWIPS with 56 meter resolution. So these 3 sensors are there, and you will get optical images, colorful images like this. You can see down, you can see forest area, agriculture area, river system. Okay, all these information you get from this type of satellite. We have a microwave satellites like ReSat-1. It has a C-band SAR, and you get during flood season, during cloudy condition, you get a very clear image of the earth, where is the flood. Okay, we have a Cartosat 2 and 3. It gives you, lot of information, high resolution data. Like individual buildings are visible. You must have seen Google Earth. You are seeing individual building with 45 centimeter. Now we have a Carto 3 with 25 centimeter. You can imagine you can see the part of the building using this type of satellites. They are very good for cartographic mapping. But there is another satellite, which is Cartosat 1, which is having 2.5 meter, but it has it generates stereo pairs. So you generate the 3D. So you can see a 3D. You can generate the 3D map of a terrain. This is the beautiful 3D map of our famous Badrinath area. Okay, so you can see this is the Satopant Glacier and all. So this type of 3D you can generate using this Carto 1 DEM. In fact, in hydrological modeling, DEM, digital elevation model, is one of the most important parameter. Without knowing what is the elevation, what is the slope, what is the flow direction, you cannot find out where water is going. You cannot model the hydrology. So for hydrological modeling, digital elevation is very important, and Carto 1 provided DEM for hydrological modeling. There are, but the ocean satellites like OceanSat 2, it has ocean color spectrometer, then altimeter also. So what it does, it provides you, potential fishing zonation, the wind direction, wind velocity in the ocean. Okay, then sea level rise also using Sorel-Altica. So this ocean information you get from this set of satellites. And of course, for weather, you are aware that Kalpana is a very famous satellite. But we have INSAT 3D, 3DR currently. Whatever image you are getting, for example, this is the image in the morning I have taken, and this is from INSAT 3DR. Okay, so these are the set of the satellite which we are using for hydrological modeling, not only hydrological, water resource management in a broad term. I hope it is clear to you. Let us move further. So when we talk about geospatial technology for water resource management, I always tell 3M. I say MQ. What is this MQ? MQ means mapping, monitoring, modeling. So mapping means mapping of a reservoir, any water body. Mapping of land use land cover like agriculture area, like forest area, like urban area. So this is mapping. Next is the monitoring. I have to monitor the water resources. For example, this is the dam. You can see after monsoon in the month of October, full of water. You can see the black color, it's a water basically. And in March, we compare with the October with the March, you see the water body decrease. So where that water has gone, it has gone for irrigation or for drinking. But if you see the June, compare this and this, June completely you can see water reduced to very minimum level. Okay, so that's how you can monitor the water sources. And third one, which for your course is organized, that is a modeling, hydrological modeling. Why we need modeling? Modeling we need for various purpose. I wanted to know how much water, suppose today, yesterday in Dehradun, 80 millimeter rainfall occurred. So this 80 meter rainfall occurs, then how much water is going to the river? What will be the discharge of the river? How I will get it? And that I get from the modeling, hydrological modeling. And this you will learn in next 10 days. Okay, so you can use various model, you can use lot of data from remote sensing. What kind of data? My colleagues will discuss with you, but in general, I can tell you like land use land cover, like, soil, like rainfall, or like, that drainage network. All these information you get from the DEM, all these information you get from remote sensing. A lot of data we need from field. And we have to, if it is not there, we have to go to the field. We have to collect the data where we need GPS for the location also. And once you do that, you integrate in GIS and finally do the hydrological modeling. Various equations are there. And finally, you get the hydrograph like this. But actually in the field, you can see along the river, how that river water is going up and down based on the time. And a particular cross-section, how river water, a particular cross-section water is moving up and down. So such type of scenario you can generate. You may be aware that in India, Central Water Commission, they are giving forecast. Like, okay, next 3 days, there will be, water level in Delhi, for example, Yamuna River, it will cross the danger level. In Haridwar, water level will cross the danger level. So that people will start going away from the low-lying area. Okay, so this type of modeling is required for that, and telling the people that this much flood will come, at what time this type of flood will come. Not only flood, normal water in the river. Okay, so this modeling is very, very important. In fact, we wanted to know how much snow melt is occurring and how much water is coming to the reservoir. For reservoir regulation, that is also very important during lean period. And this type of modeling will help in that also. So now let us start with very basic fundamental of remote sensing application for water body mapping. Now, you must have seen a screen on your laptop. This screen is having some imagery. 4 imageries are there for a specific purpose. You can see some water body. What blue color is seen here, it is basically water body. Carefully you see this. I'm not speaking now for 1 minute. You look at these 4 images carefully. Okay, you must be seeing what you are seeing here, a reservoir. What you are seeing here, another small reservoir. These are the small lake, pond, small ponds you can see here. Okay, in this image you can see all snow. So snow is white. In this you can see a lake pond with lot of phytoplankton. In this image you see a lake or a pond with sedimentation and some little bit vegetation or phytoplankton. So what you see here, you can map the water body using the remote sensing data. So in optical data, water body, if it is deep, clear, it will be black. If it is not deep and clear, it may be bluish, cyan color, like this. Another thing, carefully if you see, you can see a canal. It is coming from here. Carefully if you see. And it is linked to this. But in between, you can see the branches also. Carefully if you see. And along the branch, you can see nice agriculture area. So this is the mapping. In a first instance, you can say, using the remote sensing data, I can map the water body. Clear? It is a water body or cryosphere like a snow. Okay, So in general, I can say remote sensing and GIS for water source assessment management. What you do, you can do the water body mapping and monitoring. So reservoir mapping, water body means reservoir is also water body. So reservoir mapping and monitoring, lake mapping and monitoring, ponds mapping and monitoring, river system mapping and monitoring, irrigation water mapping, management, infrastructure mapping, crop water requirement, irrigation water management, snow cover and glacier mapping and monitoring, snow cover change, glacier retreat, glacier mass balance, hydrological modeling and flood modeling, river discharge assessment, flow routing, climate change impact on water resources, flood inundation, flood early warning system. All these things you can do using the hydrological modeling. In fact, in detail, our faculty will discuss with you about all these aspects. And of course, topography, DM generation, you get from the remote sensing. So what are the direct information you get from the remote sensing? Suppose we are talking about the precipitation. You get the cloud cover, you get the cloud top temperature, you get the cloud motion vector, you get the outgoing long wave radiation, and it gives you some information about where is the cloud, okay, in which direction it is moving, what is the velocity of the cloud movement, wind at the cloud level, all these information, evapotranspiration. So directly you are not getting, but some information you get like land surface temperature, albedo, leaf area index, normalized difference vegetation index. These information required to calculate the evapotranspiration using the energy balance technique. Water body, directly water information about the reservoir, lake, ponds, flood you get. Soil moisture, surface soil moisture you get, not the subsurface. Topography, you get the DN. From that you can get the slope, aspect, flow direction, flow accumulation. And water demand, crop acreage, crop water requirement, irrigation water. Now let us come to the rainfall. So how to estimate the rainfall? I need three kind of particular bands. Visible band, I get the type of the cloud. Thermal band, I get the cloud top temperature. Microwave sensor, I get the rain amount and the rain. Inside 3D and 3DR, they provide information in the visible and thermal. So visible band and thermal band, I get inside 3D and 3DR. While TRMM, nowadays GPM, Global Precipitation Mission, you have a microwave data. Now, inside 3D, it has a 6-channel imager. In visible band, it has, and thermal band like 10.3 to 11.3, 11.3 to 12.5. It has a sounder also, which gives you information about like every kilometer or what is the temperature and humidity, all these information. Look at this. So you can see this image directly. You can see in IMD website. This image in the morning when I was preparing this lecture, you see here, date is 19 July, today only. Time is 11:30 to 11:57 IST. So morning around 11:30 to 12 o'clock, this is the image. This image is at 10.8 micrometer thermal band. So low temperature basically means white here. So low temperature means thick cloud. You can see here, whatever bright is a cloud. First of all bright is the cloud. Number one. Number two, now you can see here, this is Delhi, this is Simla, this is Dehradun, this is Srinagar, this is Leh, this is Jaipur, this is Jodhpur. You can see all these cities are under thick cloud. So I am sure there must be raining, or either there is a cloud or there must be raining. If I am having it, so this information directly you get from the remote sensing. But if we calculate this image into the cloud top temperature, then I can say if cloud top temperature is less than minus 40 degrees centigrade, it is 100% raining there. Because with so much low temperature, vapor will condense and it will start raining. Okay, so this type of information we get from the remote sensing data. You can download, you can go to IMD website after this lecture and you can see such type of images. Generally, they are putting every half an hour these type of images. This is from INSAT 3D data. Okay, But then, as I told you, there you will get qualitative assessment of the cloud and rainfall. But here I need actual amount of the rainfall and rain rate. For that, there is a famous TRMM satellite. Nowadays we are using GPM. So TRMM was having mainly precipitation radar. It is an active microwave radar. It sends the signal, and whatever back is scattered depends on the amount of the rain, and it captures that. But you may ask me, the satellite is basically in the morning or in the evening it will pass through, but rain occurs whole day. For example, in Dehradun, it starts in the evening, and till now continuously it is raining. Now the satellite will pass only one time. So how I will know the total amount of the rain in Dehradun? So I have to club this information with the data of the cloud. Okay, which I will get from INSET 3D or 3DR. But then now there is a consortium where many countries launch the satellite. India is also part of it. That is known as Global Precipitation Mission, where many satellites are there. For example, GPM, main core observatory, which is launched by NASA. But India, we have launched another satellite, Megatropics. So like many countries, and these satellites are moving around the Earth. So you will get a lot of information from this satellite with, INSET kind of satellite with field observation, and we generate the map like this. You can see here. So you can see here, this is the map generated for India, and you can see this is a 3-day map. So this type of maps you can generate using this kind of data. Okay, now this is the reservoir monitoring. You can see Terry Reservoir in Uttarakhand. You know that this is one of the biggest dam of this country, and if you see the Rockfield Dam, this is the biggest. Otherwise, there is another concrete dam is a Bhakra, but this is a Rockfield Dam. This is the Terry Dam, and dam is here. You can see, and this is the water spread. So after monsoon in the month of December, this is a 2017 image. This is the spread. But in the month of February, you compare here and here, it is reduced. And in the month of April, it is further reduced. So this type of monitoring you can do. But what is the advantage of this type of mapping? One example I'm giving you. Pune city. So near to Pune city, there are 4 dams. One is the Temgar Dam. Another one is the Varsgam Dam. Another one is the Pensed Dam. Another one is the Khadagwasla Dam. And if I monitor these dams, I will find out which dam can send the water to the city for the drinking water or recreation purpose. So these monitorings are important not only for recreation or irrigation. This is also important for the drinking for any urban area. Okay. Now next is the flood inundation mapping and damage assessment. Modeling part after today only, it will start. Tomorrow onwards, it will start. But I am giving you some broad ideas of total water resources. Flood modeling, there is a separate lecture. So I am talking about mapping. So flood mapping, so you can see here water body, all black, so this is not the flood. But same water body, some other water body is here, but it's not black. Why? Because this water is full of sedimentation, shallow water full of sedimentation. So this is not the deep water, this is basically flooded water. So flooded water cannot be black or blue, it will be cyan color. So that's the basic difference. There is another problem. Whenever there is a flood, there will be a cloud. Right? You are aware. So look at this. This is one classical example. You can see optical data cannot penetrate into the cloud. It appears like this. This is the optical image. So what to do? We can take a microwave data and you can see flooded area. This is the river and flooded area is visible. Okay. So this kind of information we get from the, so when you are not using the optical data, which are because of the cloud, then use the microwave data. And for India, we have a RESAT-1 satellite. Very soon we may have RESAT-1A, 1B, advanced kind of satellites. And so what we do, whenever there is a flood, we capture the data. Now, this is another example of capturing entire state. Look at this. This is the Assam state. and in a single scene only it is captured. And this is the BIPS data of 810 kilometer swath. Okay, so you can see flooded river Brahmaputra along with the flood. If I can take out one district, it will be very clear to you. So this is the Marygaon district, and this area is flooded. If you superimpose over the village, you can see how many villages are affected in this district. If you see this image, it is not, that because of complete state, so you cannot visualize. But I have taken out only Marygaon district. And you can see Marygaon district, half of this, and then you can see villages. And this is a photograph of a village, and this maroon village in, this is not Marygaon, Morrigaon, sorry, this is a Morrigaon. Okay, so Morrigaon, and this Morrigaon you can see here, lot many villages. In fact, if you count it, it becomes 465. So what is this? This is the integration of remote sensing data in GIS. In GIS, I get the district boundary. In GIS, I get the village boundary, and I superimpose over the satellite data, and I get the how many villages are affected. Suppose in my GIS environment, I am having the name of the village, then immediately I can pass in on to the district collector and relief commissioner that these many villages, this is the name which are affected, kindly go for relief and rescue. Okay, but then you have to go for damage assessment. Look at this. Before cyclone, you can see perfect rooftop, and after cyclone, complete rooftop is destroyed. So this type of mapping you can do, but what kind of data you need? You need a data of submit resolution. So which data you will use? You can use Cartosat 2E data, or which is having 65 centimeter resolution. Monitoring of the flood, you can see here, day 1, flood is there. Day 8, flood is there. Day 15, flood is not there. You see the black color here, gone. Look at this. Day 1, flood is there. Day 8, flood is there. Day 15, flood is not there. Sorry, flood is there. You can see all three, like up to 15 days. In fact, this flood was there for 2 months. So you can imagine. So this is the way how you can monitor the flood. Snow belt and modeling. For that, actually, that generally in India, in this part, not all over the world, that winter starts in the month of November only. So after November in hilly area, snowfall start. Snowfall will be there, so snow cover area will increase. December it will further increase. January it will further increase. February it will further increase. After March it will start, because summer starts, so it will start decreasing. So you can see here, you can start with the October. It's a minimum. Generally in the month of October, we have a minimum snow cover area. This is the Beas Basin of Himachal Pradesh. November, compare this to this, increases. December, increases. February, maximum. May, decreases. So now where this snowfall decreases, where it has gone? It is melted and it has gone to the river. So this I have to model. May to June, further decrease. June to July, further decrease. July to September, further decrease. October, minimum. Again, it starts increasing. So what I will do, I will generate a snow depletion curve. Now concentrate here on this blue line. In the month of October, it is minimum 0% of snow cover. In the month of February, 84%. In the month of September, almost 0. So you see it increases up to 84%, then 0. So now this input is very, very important to calculate the snow melt. So you can, the density of the snow and all these things. If formula you can use, convert this snow melt into snow cover and density into finally to the snow melt. So this is the equation. No need to think about this equation. Equation needs some important parameter, which is basically how much snow cover area is there, how it is depleting, temperature, change in the temperature, rainfall, all these information, it is needed, you put into that. But from remote sensing, what I get? I get the digital elevation model. With that lapse rate, I can calculate the temperature, number one. And number two, another thing I get is snow cover area. Every week, what is a snow cover area? And I put in the model and I get a discharge versus time curve. You can see here, look at this, actual pink color is actual, blue color is the estimated, and it is so close. So this type of modeling you can do, but for that you need accurate snow cover area, and accurate snow cover area only you can get from the remote sensing data. So what we are doing, we are generating from 2000 snow cover area, SCA means snow cover area, every week using the AWIPS and MODIS data. Every week snow cover area of Jammu and Kashmir, Ladakh, Himachal and Uttarakhand, all 4 states. Okay, Jammu and Kashmir, Ladakh, Himachal Pradesh and Uttarakhand. We are generating snow cover area. You have this snow cover area already in your GIS environment. You have this DM. Run the model and you can generate the hydrogram. Okay, so this is a utility of this hydrogram. Now look at the glacier, how beautiful it is. It is using the microwave data. You can see snout, you can see ablation zone, you can see the accumulation zone. So this type of information about the glacier you get from the remote sensing data. Nowadays you must be hearing about the GLOF. There will be a separate lecture on it. So glacier lake you can monitor using the remote sensing data. 76, this is the size. 90 size increase. 2009 it is further increase. When any glacial lake size increasing means it's a danger lake, you have to monitor. Otherwise there will be a GLOF. Soil moisture, using the any passive data you can take or microwave active data. You can see here blue color means good moisture, red color means very poor moisture. You can see the Rajasthan, just a month of July, poor moisture. But you can see this Madhya Pradesh, Chhattisgarh, all this, CTCZ zone you can see here. Very nice. Or in Gangetic Plain, initially month of July, it is not there. But you can see a later stage, it started giving a lot of soil moisture. Okay, in fact, this was a 2009, I think it was a drought in this Gangetic Plain. That is the reason why you can see dry period. Irrigation water management, you get infrastructure mapping, crop water requirement, you can evaluate the performance. Okay, again, I will give you 1 minute. You see this image and tell me, I think you cannot speak from your side, but try to understand and I will explain. Okay, so in this image you can see Ganges river, this is the Ganga, and this is Haridwar city, very small, I think may not be visible. This is the Ganga river, this is the Bhimgoda barrage, and this is a diversion. Those who have seen Haridwar and Dehradun, they must be aware. So this is the upper Ganga canal. Okay, but you can see some rivers, they are the seasonal rivers passing over the canal. So when river is flowing over the canal, carefully if you see, canal is not crossing the river, river is crossing the canal. So what kind of structure you need? You need superpasses. But with this 23.5 meter imagery, you cannot see, you can just interpret it. But if you have a high resolution data, you can see this. So I will show you. With 5.8 meter, you can see distributary and minor. Yeah, this is a 65 centimeter quickwear data, and you can see the Bhimgoda barrage. Same area. With 23.5, you see Bhimgoda barrage. This you interpret it. There must be some barrage. But if you see the 65 centimeter, you can see very nicely barrage and diversion to this canal. This is the road which is going from Dehradun to Haridwar. And these are the bridge from this side to this side going to the Haridwar city. This is the Haridwar city. Now Haridwar city is visible. This is the parking area. If you want to go to take the holy dip in Haridwar, then you have to park your car here. Okay. So all these things are visible with 65 centimeter. And you can imagine our 65 centimeter vision satellite, Cartosat 2E. And with 25 centimeter, Cartosat 3. Okay. Branching of the canal is visible. This is what? Super passes. River is flowing over the canal. So this is the super passes. It means what? You can do the infrastructure mapping of an entire canal command using the remote sensing data with high resolution. So based on this, a project was given by Ministry of Water Resources to ISRO. Mainly NRSC was responsible. And this project was basically assessment of irrigation potential created using the in AIVP, Accelerated Irrigation Benefit Program. So phase 1, 53 projects were completed. Phase 2, 50 projects were completed. Phase 3, now they are doing. And we have taken 2 projects, Upper Ganga and Madhya Ganga Canal, near to Dehradun only, near to Haridwar. And we have completed this task. So you can see how we have done. You can use the high resolution data. In fact, we have used Carto 1, but you can use Carto 2 now. And you can complete this type of task. Advantage is you can find out what are the gap areas and what are the causes also. Is this because of the some litigation problem? Is this because material is not available? Is this because some village is coming in between? Is this because of some problem in the aqueduct or some structure which you have made? All these things you can assess using the remote sensing data. Remote sensing for watershed monitoring. You can see here satellite imagery. You can see a pond actual field photograph. This is the contour trenches. You can see real field photograph. This type of monitoring you can do. Check them. Here it is not there. Here it is there. Before project it is not there. After project, check them is visible. Before project, after project. So this type of information you can monitor the watershed. Bunding before project, after project. Now let us come to I will spend around 10 minutes on this. Of course, next 9 days will be on this only, but I will spend just 10 minutes on this. And this will be the last. So 4 or 5 slides are there. Hydrological modeling. So what is hydrological modeling? Hydrological modeling is defined as the mathematical representation of hydrological phenomena. Why hydrological modeling? First of all, to understand the entire hydrological process. So what is the hydrological process? Hydrological process starts from the rain, precipitation. It may be rain, it may be snowfall. Okay, so rain. Then interception because of the forest, because of the agriculture, because of the building. So land is land cover. Interaction with the rain. Then coming down, interaction with the soil, infiltration. Then going further, subsurface flow, base flow. Then coming out to the river flow. So to estimate the flow in the river. Third one is to estimate the inflow of water in the reservoir. How much water is coming in the reservoir? So that you can release the water accordingly. How much water to be diverted for the irrigation? How much water is diverted for hydropower, drinking water and recreation purpose? For that we need hydrological modeling. Generation of scenario for future water availability. Suppose in next, let us say in 2050, because of the climate change, rainfall decreases. Then how much, what will happen? How much water will be available? This you will get. What will be the impact of climate change on water resource availability? That also you can calculate. And if you know that now, what will the irrigation water requirement? What will the impact? For example, let us say temperature increase. Let us say precipitation decreases. Just one example. Then you can calculate how much water will come in the river. Number one. Suppose temperature increases. Then crop water requirement will increase. Demand will increase. So this type of analysis you can do, and you can go for effective water management. For that you need hydrological modeling. And finally, flood forecasting and prediction. And our next 9 days focus will be on all these aspects. So this is one example. We have covered all 20 river basins of India. This is one example I'm giving you. We have divided entire country into grids, all 20 basins. This is one example of one basin, Pennar Basin and nearby basins. And you can see the hydrological model we have taken. We have taken variable infiltration capacity model. I'm not going into detail. There will be separate class on that. Each grid having subgrid variability of different land use land cover from remote sensing data. So from remote sensing data, I get the land use land cover like vegetation, soil, discharge elevation model, and rainfall information. Many information I get from the remote sensing. Many information I get, for example, rainfall from AWS, field data. Okay, soil map from somebody else like NBSS LUP. All these data is integrated in the GIS environment. Finally, hydrological model is run, and I get surface runoff, evapotranspiration, soil moisture, and base flow. Okay, for all river basins. So this type of modeling we are doing. A lot of remote sensing GIS data is required for this. So this is the example. We have already run this model for 15 years, 91 to 2005. Now we are working on 2006 to 2020. This paper is already published in Current Science. Those who are interested, they can see this paper very nicely. Now this is now 15 years. So when you see January 1, 1991. So every day, 365 days for 91, 365 days for 92. Like that, 15 years into 365. Every day, water balance for all 20 river basins of country, we have calculated using this type of model. Now, flood modeling. So this is one example. This is the Terry Dam, and this is a downstream. You can see. So we have calculated different scenarios. If this much water will be released from Terry Dam, what will happen in the downstream? Okay, so look at this. This is the Bhimgowda Bera, this is Haridwar city, and downstream, and you can see if how the discharge will change with respect to time. So this again from flood modeling or hydrological modeling we have done. So this type of scenario you can generate. This is last slide. This is famous Kerala flood. This is our modeling, and this is the actual field photograph. You can see our modeling. This color is showing. Okay, and this is the actual field photograph. This is our modeling, and this is the actual field photograph. So this type of information modeling you can do using the remote sensing and GIS. What is important? Important is lot of input data is required from remote sensing. Lot of input data you create in GIS using the field data and GPS. Integrate everything into GIS. So GIS is a two-way. First, we provide all inputs into the GIS. Then whatever is the output of the GIS put in the hydrological model. Then again, hydrological model for visualization. For example, if I want to visualize this type of scenario, 3D model. So for that, again, I have to come back to the GIS and generate the 3D model, and we visualize this kind of scenario. So this way we complete the hydrological model. So this is my last slide. Thank you very much.